next one. Oh, rats, it closed my paint program. Let me open it again. Okay. Okay, number one. A power plant produces a voltage of 110. What's the maximum voltage? If it's AC is 110. So, yeah? It's okay?
No.
So, its voltage goes like this, and on average it's 110 volts. I want to know what the maximum is. Do you remember what the formula is? It's V average equals V max over root 2. So it means V max here will be root 2 times 110. So what's that, please? 1. Thank you. Okay, next one. Yeah. Now, this one here, you have a 1 meter copper manhole. It lies on the ground. A person rotates it 180, then lifts it up and slides it along the ground. It takes 2 seconds to rotate the cover and 3 seconds to lift it up, and then 4 seconds to slide it across the ground. What is the induced EMF in the pipe? Sorry, should have said in the manhole, due to the Earth's magnetic field. So we need to think in the process: rotate, lift, slide. Which stage produces the current? So this is a little bit similar to the example with the plane that takes off. Remember we did this example? Yeah? So it's the middle stage that gets the current. And the formula here you could use is, you could actually just use BLV. That's a formula you could use here. The B is 0.07 times 10 to the minus 3. The L is 1 meter. And the V, now the V is a little bit tricky. You have to think about what the V is. What's the speed? Well, you have to work it out. So it's distance over time. So it moves a distance of 3 centimeters in a time of 3 seconds. Two or 3? 2 to rotate, 3 to lift, 4 to slide. Yeah? I think it's just the lifting one, Matt, which is the second time. Is okay or not okay? Are you sure? Bum, 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 bum. What's that going to be? 700 nanovolts. No. Yes. 700 nanovolts. Is that okay? Can I scroll down? Number 3 is you have a pipe which is 2 meters long and you drop it 100 meters. What is the induced EMF? So again, this is BLV. That's 0.07 times 10 to the minus 3 times 2 times the speed. Now the problem is the speed is not constant. So what we could do is we could use the average speed. So the average speed would be distance, which is 100, divided by time. So we need to work out what the time is. Yeah. So if I use UVATS, U is 0, V we don't know, A is, we'll keep it positive down, 9.81, T we don't know, S is 100. S equals UT plus a half A T squared. So the T is square root 100 over 4.905. Okay, so what answer is this? By the way, if anybody's wondering, you can use the other formula too. It's a little bit trickier to use it. Yeah? Continue? Oh no, sorry, I need the answer. Actually. Ten to the minus 4 volts, yeah? So that's 0.632 millivolts. It's pretty small, as it should be. Surprised it's not even 1 millivolt though. Yeah, okay. Right, next one. Next one. Yeah. So, you have a copper wire and it's wrapped in a loop like this. And then what you have is, yeah?
Oh, that's right, that's right.
what did you get on deck?
Yeah, 3.1.
Final, just 3.1?
3.1, like lots of that's
Yeah, but 10 to the minus?
3.
Oh, so 3.1 millivolts. Okay. I thought it was a bit small, Matt. 3.1 millivolts. Okay. A copper wire is wrapped in a circular loop 100 times around a magnet. So you have a magnet in here, and then you take the magnet out. And what's the induced EMF? Okay, so if we use Faraday's law, we know what the N is. What is it? It's 100. Now, what's changing here, the B or the A? Well, the A doesn't change, it's the B that changes because you take the magnet out. So delta phi is equal to A delta B. Because it's the B that changes, because you remove the magnet. Yeah? So that's 100 times A times delta B over delta T. Now, I think we know some of this. We know it's 100. we know it's pi, we know it's 5, and we know that t is 0.25, right? But what's the delta b? Well, the delta b is the b at the end minus the b at the start. And what's the b at the end? It's 0, because you remove the magnet. And what's the b at the start? It's 5. So the answer is -5. Again, I don't care about the sign, so I'm just going to put the answer in as 5, because I just need to know the voltage, don't need to know its direction. Okay, so if we calculate this, we can get the answer. Oh, sorry, I misread it. It's 2, isn't it? 2. You got this? Matt? I mean, the calculator. And do you have an answer?
Yeah, but I'm going to listen to maps.
No, he was wrong last time.
10.05.
Seems reasonable. Matt will confirm if you're telling the truth. Uh-oh, different answer? What did you get? Oh, Andek, did you use 2 or 5?
2.
Oh, okay. You got 6.28? Let me calculate it without a calculator.
Wait.
That's 400.
That's right.
Okay.
Yeah.
What was your mistake, Andek?
I'm not really sure.
Okay.
Yeah, but I redid it again. I got 6.2.
Okay, no problem. Can I do number 5? A small generator uses a magnet of flux density 5. So, okay, you've got a magnet here. Five Tesla. And it's rotating. There's a plane that's rotating. So, at the beginning, I tell you the plane is like this. And it's rotating clockwise. So that would mean in the picture there's a force acting, well, in this picture here there's a force acting to the right here. Yeah. Okay. Now, first question. Because it's moving, you get a current. But if you use your right-hand rule here, this is the force, this is the magnetic field. Small problem though. In my picture here, the force and the magnetic field are in the same direction. It doesn't, we can't, see, this is the force, this is the magnetic field, and this is the current. But in the picture, the force and the magnetic field are in the same direction. So you actually don't get a current when it's in this position. Okay? Yeah. But anyways, the first thing I want to do is calculate the flux linkage in this position. And this will be N flux. And the N here is 10. And the flux is B A cos theta. And what's the B here? 5, is it? So that's 50 and the area is 0.2 squared cos theta. And what's that? That's going to be, could you type 50 times 0.04? Is that 0.08? Is that right? 50 times 0.2 squared? 2?
Yeah.
Oh goodness, yeah, sorry. Goodness sake, Stephen. Right, let's see. 2. Are you sure?
Yeah.
Okay. Fine, okay, sorry. 2. Now, what is the theta here? What's the theta here? So if you look up, Matt, the way you measure the theta for these problems in this formula is you look at the angle between the normal on the plane and the field. So when it's in this position, what's the angle between the normal and the field? Well, they're parallel. It's the other one, 0. It would be 90 if it was like this. Then it's 90. So this is equal to 2 cos 0, which is equal to 2 Webers. Continue? Yeah. Oh, I did the 10 here when I multiplied it by the 5 to get 50. Yeah. Okay, continue. So look, in the next time when it's horizontal like this, look, you do get a current. So if I use the formula F, the right-hand rule here, in my picture the F is pointing down and the field is to the right. So if I look here, I get a current that comes out here and one that goes into the page here. So the current is going in and coming out here. That's not really important, don't worry about that. The only difference here is the theta. So when it's perpendicular, when it's horizontal, the normal is pointing up like this, which is perpendicular to the field. So like you said, this time on deck it will be 90, so it's 2 cos 90, which is 0 Webers. Okay? So now I want you to calculate the change in the flux linkage. So it goes 0 to 2. So the answer is minus 2 Webers. Oh, sorry, I wanted to calculate the time. Okay. So, if you look here, this is rotating in a circle, and I give you the frequency. And the frequency is 50 Hertz. So you know the time is 1 over F, which is 1 over 50, which is 2 over 100, which is 0.02 seconds. So if it takes 0.02 seconds to rotate once, how long would it take to rotate from a vertical position to a horizontal position? It should be a quarter of the time, because that's only a quarter of a turn, you know. So the time we care about is a quarter of this. .005, I think. Is that right? that okay? Yeah? So the last part is what's the induced EMF. So that would be minus 2. So 2 over 0.005, you know, your delta phi over your time. And that would be what exactly, please? What you get? 400 volts. Yeah? You okay? Continue? So that was induction. So the next one was pretty easy, I think, the transformer. So let's have a look at that one next.